everyone, we're Group 40. Today we will present our AI final project. Our topic is Smart Behavior Traffic Light Scheduling System. Here's the outline of our presentation. Traffic congestion is a significant issue in cities around the world. It leads to major economic loss, increased air pollution, and a lower quality of life for residents. One key factor that contributes to urban congestion is insufficient traffic signal control. Poorly timed signal can result in long waiting times at intersections and severe traffic jams, especially during peak hours. Effective traffic signal management is therefore critical to improving traffic flow and reducing delays. This is not just an abstract problem. Many of us experience this in daily life. For example, near our campus, traffic congestion during rush hour is a common and frustrating issue. In our project, we introduced new roadmaps that integrate advanced traffic simulation and control strategies. These roadmaps provide a more realistic and flexible foundation for testing and improving traffic management solutions. Our work focuses on exploring a variety of deep reinforcement learning models to dynamically optimize traffic signal timing. By leveraging DRL, the system can adapt to real-time traffic patterns, helping to reduce congestion and improve overall traffic flow. To ensure a comprehensive assessment of system performance, we employ multiple evaluation metrics. Furthermore, we designed a new reward function that incorporates passenger comfort, providing a more human-central perspective to traffic optimization. In this project, we refer to the paper, Deep Reinforcement Learning for Traffic Signal Control and Review, published in IEEE 2020. Compared to related works, our project differs in two main aspects. First, in terms of model and datasets, we experiment with multiple DRL models, including DQN, PPO, APUC, and QRDQN, across various traffic scenarios and datasets. Second, in evaluation metrics, we evaluate multiple metrics such as average and maximum waiting time and throughput, a newly designed reward that incorporates passenger comfort. We also conduct qualitative analysis to better understand model behavior and real-world applicability. For the platform, we use CityFlow, a high-performance traffic simulation engine that models detailed intersection behaviors and vehicle dynamics. This allows us to create realistic traffic scenarios. In addition, we integrate CityFlow with GIMP, an RL environment wrapper, enabling us to easily interface CityFlow with various reinforcement learning algorithms.
Next, let's talk about the dataset. CityFlow uses two main data files, the RoadNet file and the flow file. First, the RoadNet file defines intersections, roads, lanes, and how they're connected. Note that in this example, only intersection 11 and intersection 21 are actual intersections controlled by traffic lights. We also specify the allowed directions on each road, such as going straight, turning left or right, and define the traffic light faces accordingly. Next, the flow file sets vehicle behavior, routes, and entry times, helping us simulate more realistic and diverse traffic conditions. This project includes 4 different types of road networks. The first 3 are based on the open datasets. Since the original GitHub code only supports a 1x1 intersection, we modified the state and action array sizes to fit larger network like 1x3 and 2x2. State depends on the number of roads and lanes. Actions depends on the number of traffic light faces. Last but not least, we simulate the real-world intersection of Hongfu Road and Dashu Road. While the layout is simplified, it captures the key traffic movements. Some directions are blocked to reflect the actual conditions caused by nearby highway interchanges. For example, this part of Dashu Road turns right onto the highway, while the other side functions as an off-ramp coming down from the highway. In this project, we use DQN as our baseline for traffic light control. DQN is a reinforcement learning algorithm that uses a neural network to estimate Q values, helping the agent decide which action, in our case, which traffic light phase will lead to the highest long-term reward. The state includes traffic features like vehicle counts or queue length on each lane, and action represents the selection of a traffic light phase. By using DQN as a baseline, we can compare how well other reinforcement learning methods improve traffic flow and reduce waiting time.
Now, I'll walk you through the main approaches of our project, which focuses on using deep reinforced learning to optimize traffic signal control. Our goal is to reduce congestion and improve traffic flow in urban areas. We explore 3 advanced DRL models: Advantage Actor Critic, Proximal Policy Optimization, and Quantile Regression DQN. Additionally, we've redesigned a reward function to balance traffic efficiency with passenger comfort, ensuring smoother and more effective traffic management. Let's start with A2C, or Advantage Actor Critic. This is a synchronous policy gradient method that combines the strength of both value-based and policy-based approaches. In A2C, an actor proposes actions, such as changing traffic signal timings, while a critic evaluates those actions by learning both the policy and value functions. This dual approach makes training more stable and simple, efficient compared to vanilla policy gradients. By applying A2C, our model learns traffic signal control policies that significantly reduce waiting times across intersections, improving overall traffic flows. Next, we have Proximal Policy Optimizations, or PPO. PPO is a widely used on-policy RL algorithm known for its stability and strong performance. It uses clipped objective functions to keep policy updates within a safe range, preventing drastic changes that could destabilize learning. This makes PPO efficient and easier to tune, requiring fewer hyperparameters. In our project, PPO adapts to dynamic traffic patterns, capturing long-term trends to optimize flow and ensure fairness across different intersections. Now, let's discuss QRDQN, or Quantile Regression DQN. Unlike traditional DQN, which estimates a single expected value, QRDQN is a distributional RL method that models the full distribution of future returns. By predicting multiple quantiles, it allows the agent to reason about risk and uncertainty in decision-making. This is particularly useful for traffic signal control, as it helps the model handle variability in traffic conditions, leading to robust policies that perform well under diverse scenarios. Lastly, within our main approach, we redesigned the reward function to balance traffic efficiency and driving comfort. The reward is calculated as a weighted sum. We assign a negative weight to the total waiting time of vehicles at an intersection to prioritize efficiency. We also include a comfort term, penalizing abrupt signal changes by adding a small negative reward for frequent phase switches. By combining these factors, our reward design encourages the RL agent to optimize signal timings in a way that reduces congestion while maintaining a pleasant driving experience. This balance is critical for real-world applicability.
To evaluate the performance of our baseline and proposed methods, we use both quantitative and qualitative metrics to see how well the traffic signal control works. For quantitative metrics, we first consider average waiting time, which shows how long vehicles typically wait at red lights. Lower values indicate smoother traffic flow. We also look at the maximum waiting time to catch extreme cases where a vehicle might get stuck for too long. This helps us identify if congestion is happening in specific directions. Another key metric is throughput, which counts how many vehicles pass through the intersection during the simulation. Higher throughput means better traffic handling capacity. We track the total reward collected by the RL agent, which shows how well it learns to optimize traffic flow based on our design. For qualitative evaluation, we review simulation videos to see how realistic the traffic behavior looks. We check for things like vehicle collisions and frequent signal switching. Combining these metrics helps us ensure the control decisions are both effective and practical.
We conducted multiple types of experiments to evaluate our method. First, we compare different DRL algorithms. Second, we compare the original waiting time-based reward versus comfort-aware reward that considers both waiting time and acceleration smoothness. Third, we tested different learning rates. Fourth, we evaluated the generalization of our train policy across different traffic environments. First, we compared different algorithms in one-time format. For O+, the x-axis shows episodes and the y-axis shows different metrics. Starting with the reward comparison, we can see that PPO and ATC quickly reach stable and high rewards. In contrast, DQN and QRDQN show large oscillations, which means the learning is unstable. This is likely because policy gradient methods work better here. Next, looking at the throughput comparison. All methods have similar throughput, with periodic change due to bursty traffic. Moving to an average waiting time, PPO and ATC maintain low values. QRDQN improved during training but remains then stable. As for max waiting time, shows a similar pattern to average waiting time. In summary, PPO and ATC outperform DQN and QRDQN. QRDQN shows clear improvement. Now moving on the learning rate comparison on the 1x1 map. Here we compare three learning rates. For DQN, the learning rate affects both frequency and magnitude of the oscillations, and it is more sensitive to learning rate. Overall, when using 6 to 5e-5, the model shows better overall performance. This is 1x1 roadmap. It consists of a single intersection with 4 directions and 2 lanes per direction. However, the traffic lights seem to change very often. This is something we can improve in the future. Next, on the 1x3 roadmap, there is no clear improvement over training, which shows that the model struggled to learn a good policy in a more complex environment. For PPO and ATC, the performance is still relatively stable, but not as good as in the 1x1 map. This suggests that as the environment becomes more complex, it becomes more challenging for all models, and especially for value-based methods like DQN. Now, looking at learning rate comparison on the 1x3 map, we can see that DQN and QRDQN perform better when the learning rate is smaller. With large learning rate by 0.001, the results are very unstable. This is the 1x3 roadmap. We observe that straight-going vehicles are more likely to cause traffic jams. Next, the 2x2 roadmap. The result is similar to 1x3 roadmap. Overall, the increased complexity of the map makes it much harder for all models to learn an effective policy. Interestingly, the 2x2 map with learning rate 0.001, we can see that QRDQN shows a downward trend over time. DQN and QRDQN remain unstable even with smaller learning rates, and PPO and ATC are more stable, but the average waiting time is still high. This is the 2x2 roadmap. It consists of 4 intersections arranged in a group. And we also observe that intersections can block each other. Now, looking at the intersection of Guangfu and Daxi Road, which is real-world experiment. Interestingly, we can observe that DQN shows a clear downward trend in both average waiting time and max waiting time. By the end of the training, DQN actually outperformed PPO and ATC on these 2 metrics. It suggests that in a particular traffic pattern, DQN may have found a more effective policy for reducing waiting times. However, DQN throughput still remains very low. Looking at learning rate comparison on this real-world map, DQN is very sensitive to learning rate, and PPO and ATC are more stable across learning rate. This is intersection of Guangfu and Daxi Road. Compared to previous map, this intersection has imbalanced traffic flow. Now, comparing reward designs, this suggests that comfort-aware reward is harder to learn, since it balances both waiting time and smooth driving. As for limitation and future work, our experiments used a stationary environment with periodic traffic and fixed reward. Future work will explore non-stationary scenarios such as dynamic traffic and unexpected events to test model robustness. In some cases, the policy switches lie too frequently, which may cause driver discomfort. This can be improved by adding a penalty or a minimum phase duration. This is our GitHub link. You can scan the QR code to see our GitHub repo. And this is our references.